It seems unfortunate that much of what we know about the functions of specific areas of the brain is the result of observing what happens to individuals with some kind of brain impairment due to accident or injury or disease. But this is where most of the research still happens. Recent studies of children with lesions in the left cerebral hemisphere, over there, show that they have difficulty with language, particularly with grammatical structure and fluidity of production. But a child with lesions in the right hemisphere does not show this type of language impairment. Researchers now know that a child acquires his first language that as a child acquires his first language, the activity is not localized exclusively in the left hemisphere of the brain, but that language functions do eventually settle there. Okay. Cognitive differences have been observed in children who have had half their brains removed, hemispherectomy, due to disease. In a child whose entire right hemisphere has been removed, the language ability remains intact because the language stuff is over here, right on the left. But when the left hemisphere has to be removed, the child's language ability is impaired, although his spatial visual abilities remain good. Interestingly enough, even with such radical surgery and that whole left part of the brain, left hemisphere of the brain gone, the child's IQ remains the same, and he's often able to relearn parts of language, and the brain is amazing. Another area of research is split brains. These are cases in which the corpus callosum, you remember that central part there, is surgically cut in order to treat certain types of epilepsy. And it solves the epilepsy, but the result is that the two hemispheres, which were previously able to communicate freely with each other via the corpus callosum, now have to find other ways to coordinate actions and functions. What happens is that the two unconnected halves continue to function, but independent of each other. Although a message received by one side of the brain should result in coordination with a function on the other side of the brain, the path of communication between the two hemispheres has been severed. An example in your book is if an object such as a ball is put into the left hand of a split brain person with his eyes closed. Okay, he knows what it is. You know, his brain is still there, but the corpus callosum has been severed, so the communication doesn't happen. So he's got the ball in his left hand, and he knows what it is, and he knows what to do with it, but he can't give you the word for it because the left side of his brain, the left side of the body, is controlled by the right hemisphere. Okay. And the right hemisphere doesn't contain the language faculty, right? But if the ball is put into his right hand, the side of the body controlled by the left hemisphere, right? Okay, where language is, he can describe it and name it and tell you what to do with it. Okay, split brain research has provided a great deal of insight into precisely what information and which functions are seated in each hemisphere. For example, the right brain does better with spatial relationships, such as pattern matching, recognizing faces and directional orientation, music, visual art, and other nonverbal modes of expression. Consequently, we think of the right brain as being capable of more abstract cognition and creative activity. The left brain, on the other hand, controls language, perception of rhythm, ordering of events in time and sequence and math. Okay. In contrast to the right brain, we think of the left brain as dealing with linear functions, okay, and concrete thought. Dealing with verbal expression and manipulating facts, not flights of fancy as on the right side. However, simply assigning specific functions exclusively to one hemisphere or the other, the right being abstract thought and creative thought, and the left being linear and more analytical, this is just too easy. A simple answer often is too easy, and you need to explore that. Doesn't a great deal of our capacity for abstract thought, which could be on the right side, depend on language, which is over here, right? Don't you think of some abstract concepts in terms of how you talk about them, or in terms of how they are explained to you? Research on split brains provides support for the specialization on right brain, left brain functions. Because the ability to understand written language is a function of the left brain, written text shown only to the right brain, that is, read by the left eye only, left eye goes into the right brain, okay, can't be decoded, okay. So it would have to be reading with the right eye going into the left brain, okay. An interesting area of research focuses on what you hear, on how what you hear is processed through the right ear versus through the left ear. If a sound comes into your right ear, it's perceived mainly in the left hemisphere, right, of your brain. And if it comes into your left ear, its perception is in the right hemisphere. Okay, studies have been conducted called dichotic studies, where subjects with headphones were fed slightly different sounds simultaneously in each ear. Okay, for example, a nonverbal sound, such as a dog bark, was fed into the right ear, and a meow into the left ear. Okay, although both sides of the brain are involved in processing the oral input, the subject was more apt to say he heard the meow because it came into his left ear, right brain processing of abstract things, right? Conversely, if the input was verbal, okay, meow isn't verbal, okay, so that, for example, the word mat came into the right ear and bat into the left ear. The subject was more apt to say he heard mat in the right ear because it was processed on the left, okay, on the left, in the left hemisphere. The theory to explain why this happens is that although the subject can understand what both the sounds are, they are quite aware of what both the sounds are, the side of the brain where the sound is initially processed takes over in deciding which sound to report or word to report. Another type of research called event-related potentials, ERP, involves attaching electrodes to a subject's head to monitor the electrical activity of various parts of the brain in response to different stimuli, both linguistic and non-linguistic. For example, if a sentence read to a subject makes sense, the brain activity follows a fairly predictable pattern and timing, okay? For example, the pizza was too hot to eat, so we know where that's going to be processed and how much time it takes. But if the sentence doesn't make sense, such as the pizza was too hot to laugh, okay, more brain activity is required in some areas, and as a result the processing takes longer. It's not logical. It's not a pattern that we've even thought of before, right? A final bit of language processing research given in your text illustrates the difference between types of visual processing in readers of Japanese. Japanese writing employs three systems intermixed: two syllabaries, symbols representing specific sound combinations, syllables, and many Chinese characters, ideographs, the meanings of which are representational. Okay, if a reader of Japanese has damage to the left side of the brain, he has trouble reading the syllabaries, okay, the linguistic elements. But if the damage is to the right side of the brain, he struggles with the Chinese characters, which are the visual representations of concepts, complete concepts. Interesting stuff.